this is Priyadharshini working as an assistant professor in the Department of Artificial Intelligence and Data Science. Today we are going to discuss the topic asymptotic notations. So what is asymptotic notations? In mathematics it is also called asymptotic notations, or also called as asymptotics, which is a method of describing the behavior of a function, which describes the behavior of a function. In computing, asymptotic analysis of an algorithm refers to defining the mathematical foundation of its running time performance based on its input size. For example, if the time of one operation is computed as f of n, and maybe for another operation if it is computed as g of n square, this means the first operation running time will increase linearly with the increase in n as well, and the running time of the second operation will increase exponentially when n increases. Similarly, the running time of both operations will be nearly the same if n value is very small in value. So, usually the analysis of an algorithm is done based on three cases. First one is best case, which is omega notation. Second one is average case, which is also called as theta notation. And the worst case, which is big O notation. So all of these notations we are going to discuss in detail. So let's take omega notation. So first we define what are all the notations given. So big O notation, it is asymptotically less than f of n, whereas f of n is less than or equal to g of n. The next one is omega notation, which is asymptotically greater than f of n, that is f of n is greater than or equal to g of n. And the last notation is the theta notation, so it is asymptotically equality, so which is f of n is equal to g of n. So this is the basic notation. So now let's see about the big O notation, or we'll see the worst case analysis of big O notation. So big O notation, as the explanation goes, f of n is equal to order of, that is big O of g of n, when there exists positive constants c and n naught such that f of n is less than or equal to c into g of n for all n greater than or equal to n naught. That is, if f of n is equal to order of n squared, then f of n can be larger than n squared times, but I can choose some constant c and some value n naught such that for every value of n larger than n naught, f of n is always lesser than cn square. That is, for larger values than n naught, f of n is never more than a constant multiplier greater than n square. So this is the definition of big O. So this will be the visualization of order of g of n. So in simple, I'll tell you, order of g of n is equal to f of n. There exists positive constants c and n naught such that f of n is always less than or equal to c into g of n for all n greater than or equal to n naught. This means f of n is equal to order of g of n if there are positive constants n naught and c such that to the right of n naught, the f of n always lies below of c of g of n if we visualize it carefully. The next one is big omega notation. So big omega notation, as I told you, will be the best case notation. So it is asymptotically lower bound of a function f of n for a given function g of n. So the definition goes like this: for a big omega notation, f of n is equal to big omega of g of n if there exists a positive constant c and n naught such that 0 is less than or equal to f of n and it is greater than c into g of n for all n greater than n naught. And n, for example, if you take n square is equal to omega of n, then c is equal to 1, n naught is equal to 2. So for all n greater than 2, n square greater than 1 into n. So this will be the big omega notation. So the visualization visualization representation of big omega notation is given. So I'll tell you in detail. So if you have to calculate the big omega, so you have to break the program into the smaller segments, find the number of operations performed for each segmentation, add up all the operations and simplify it, remove all the constants and choose the term having the highest order of any function, which is always less than f of n, which tends to infinity. Let's say it's g of n, then omega of f of n is omega of g of n. The next one is theta notation. So big O is not a tight upper bound. In other words, n is equal to order of n square. Theta provides a tight bound. That is, f of n is equal to theta of g of n if there exist positive constants c1, c2 and n naught such that 0 is always less than to c1 into g of n, which is directly less than or equal to f of n, and this f of n is also less than or equal to c2 into g of n for all n greater than or equal to n naught. So let us see the visualization representation of theta of g of n. So c2 of g of n will be the upper bound, f of n will be lying lower to that, and c2 of g of n will be lying slightly lower to that. So these are about the various properties of asymptotic notation.